last speaker is Dr. David Waddington, and the title of his talk is Real-Time Deployment of Open Source Tools for Image Reconstruction.
All right, thank you. I will share screen. And okay, all good?
Yeah, all good, can see it.
Yep, all good. Yep, cool. All right. Thank you. Yeah, good to see some familiar names in the participant list, and thanks for showing up this talk, and thank you to the organizers for the invite. So yeah, I'm going to talk to you today about some of our work integrating some tools for real-time use, in particular open source tools with some image reconstruction work, but also a little bit further from that, looking at acquisition and quality assurance and things like that as well. Want to acknowledge that the University of Sydney is on Aboriginal land and pay our respects to their elders past and present. And this work is performed on the Australian Aboriginal lands of the Gadigal and the Darug people. Okay, so let's start. Okay, we know, if you don't know, you should know, compared to most other imaging modalities, MRI is really slow. Now, why is it slow? Well, it's because we're sampling this kind of abstract thing called case-based, sort of the spatial frequencies, and then we perform this image reconstruction, usually through some form of a Fourier transform. But sampling each of these case-based points needs to be done discretely in a unit of time, and that leads to long acquisitions. And then beyond that, and so that means we need to sweep gradient values, measure each of these points individually. Now, there are techniques based on undersampling, compressed sensing that speed things up, speed up the acquisition, but these also typically then require more computationally intensive reconstructions, and that leads to slow reconstructions. Also, errors can accumulate and things like that if you leave out too much data. So what we've been working with in particular is a tool known as the Gagatron, which might be familiar with some of you, to speed up our acquisitions. Now, before we jump into that, I'll give some context of what we're actually trying to do. So James touched on the last talk on radiotherapy and MRI. So I'll take a different perspective here. Why does radiotherapy kind of need MRI? Well, radiotherapy is about 50% of cancer patients. And conventional imaging during radiotherapy has atrocious soft tissue contrast. And that's because it's all X-ray based. And we all know X-rays are for bones. This is an MRI audience. We know that MRI is great for soft tissue. So if we compare something like a prostate tumor, you can see a typical CT image of a prostate has this really even grey tone, whereas within that same prostate with the MRI, you can see the tumor, you can see all this fine structure. And so for the delivery of radiotherapy on the day, it's typically been based on CT. These new systems that are coming out integrate MRI to sort of more accurately guide that radiotherapy. So this is kind of the entry of the MRI Linac. So the MRI Linac is basically taking two things that should never be combined, which is a giant magnetic field and a huge piece of steel in the form of a linear accelerator, and putting them together into one system. And there are a few of these out there now. Globally, we've seen that integrating this MRI with the linear accelerator, the Linac, it's been done by a company called Meridian, by Vuray, their system, the Meridian. So they sort of first treated a patient in January 2014. It's based on a cobalt source then, but since upgraded to a linear accelerator. And since very recently, which I won't touch on, a bankruptcy for that company. So, but things are still great in the MRI guided radiotherapy world. Let's keep that smile going. And then separately, there's this Unity system by Electa. And so these systems in early clinical trials have been showing some really promising results. So depending on your study, acute treatment toxicities could be reduced by more than 40%, which is a huge change. I think in this case, I'm talking about prostate treatments, but the clinical data is still early, but there's some really promising stuff showing that you'll get a better cancer treatment on an MRI-guided radiotherapy system. Now, the thing is, thinking about developing technology for these systems, there's a lot of stuff in the background. So this Meridian system works on a Siemens MRI console. The Unity by Elekta works on a Philips MRI console. And we work on something else entirely. In Sydney at Liverpool Hospital, we have something known that we call the Australian MRI Linacs. So this is a really bespoke system. We've got a split bore 1 Tesla MRI system, and then we have a 6MV linear accelerator here that goes through a hole in this wall into the magnet. This is running now from an open source perspective, from a development perspective. This is a really beautiful system though, because it means that it's the nuts and bolts are all there. We can change anything. We can install different bits of equipment. And in this case, we're running on a Siemens MRI console for the MRI component, but all custom gradients, custom magnets, custom RF coils. Now, what do we need these systems to do though? And this goes back to where I said before, MRI is a bit slow. So we imagine here we have someone with quite a central tumor, so it's quite close to the heart. We want to deliver radiotherapy beams to this tumor very accurately, but we absolutely want to minimize collateral damage to the tissue that surrounds this tumor. And ideally what that means is we want to be able to adapt our treatment and our radiation beam to the movement that we're seeing there. So you can see there's two main things. There's movement of the diaphragm and there's movement of the heart. So we're kind of talking here cardiac motion on the order of 1 hertz, respiratory motion on the order of 1/4 of a hertz, or a breath every few seconds, every 4 seconds. And we want to track that with millimeter level accuracy. So it's quite a challenging technical issue. And it's something where it's kind of on the edge of what MRI is capable of. So to flesh this out a little bit more, what does real-time adaptation look like on one of these systems? So in looking to minimize that treatment toxicity, what we want to do is use this device that's known as a multi-leaf collimator for the purpose of this talk. This is just a beam shaping device. It's a beam moving device. And then we have this moving target. So in this case, a lung tumor, for example, it could be a liver tumor. And we want to really adapt the beam to that moving target. We want our beam to be as small as possible, so we minimize collateral damage, but also as accurate as possible, so we still ensure that the tumor receives the full treatment dose. So in practice, the way that we kind of implement this on our system is we designate some sort of region of interest, and then we use some sort of tracking algorithm to frame track that movement through template matching in this case. For these treatments to be effective, we really need what we call the end-to-end system latency to be below 300 milliseconds. So what that means in practice is that tumor moves, it gets imaged, it goes through some sort of processing pipeline that adjusts where the beam is going and moves the beam to track that target. So the time from that movement to the beam moving to adjust needs to be 300 milliseconds, but there's a whole lot of stuff that needs to happen in between. So to flesh that out a little bit more, a typical experiment we might run using these little tumor phantoms here. So we have a moving platform. These are programmed to move as if they're undergoing respiratory motion. We can then image them on our 1 Tesla system with Cine MRI, and then we can adapt in software these beam shaping leaves, or the multi-leaf collimator leaves, and then using a radiation imaging device, electron portal, dosimetry device, we can actually see where did the radiation go, and we can actually sort of, in the contrast there is a little bit of that ball that we're imaging. So we performed this with a simple experiment. We can see over here that we're getting sort of 330 milliseconds end-to-end latency. And so while that, I guess, might be, you might say, okay, I said earlier, less than 300 milliseconds is good. You can see that the quality of these images is not very good. It's very low resolution, very simple task that's going on here. And we can see that about 200 milliseconds of that 300 milliseconds is the actual sort of MRI component of what is going on. So the acquisition, the reconstruction of that data. And just to say on sort of the state-of-the-art clinical systems, it's not that much better. Sort of 250 milliseconds for one 2D slice. So this is one example here. And really, we want to be tracking in 3D in real time for these treatments. So how are we going to do that? Well, we all know sort of the magic of AI that's been coming out, all of the advances, the great power that comes from that. So these neural networks, one of the things we don't speak about a lot is that once they're trained, they are really, really fast. So they can reconstruct and process images in a single forward pass. So the vision here is really to kind of harness that power of AI and integrate that into the MRI scanner workflow here. So we're imaging, we're then using AI for whatever task we need to achieve, whether it's reconstruction, image enhancement, segmentation, and then using that to adapt our beam shaping device to track the tumor. And so I guess this is where sort of this Gadgetron tool has come in. So we have the Siemens platform. We said, okay, how can we do this? How can we implement our neural networks onto this system? And the Gadgetron is a really kind of nice platform, originally largely put together by a group at the NIH. And what it does is it bypasses the vendor reconstruction chain. So what you do is you compile a little bit of code and you insert this into the vendor reconstruction chain. And then you bump out of there onto an external pipeline where you can process anything on a high performance computer that's adjacent to the MRI scanner and perform once the data's out of the MRI scanner, you can do what you like with it. And this happens really quickly in sort of tens of milliseconds at most. In our case, we've written additional code here that allows us to sort of essentially deploy any neural network we want for our image processing once it's acquired. And I do want to make the point here that really on the MRI scanner, all it's requiring is this installation of the emitter injector software. So on the Siemens platform, this is something known as the ICE Gadgetron. But also for those of you that are using, in particular, some of the more recent platforms, you should have a look at. So Siemens has introduced an open recon tool that essentially performs a lot of these operations for you with a lot less involvement on your part. And also there's the FIRE tool that has also aided sort of these reconstruction efforts. In our case, we've implemented the Gadgetron. Now, something else that most of these things are also relying on, and just more of, I guess, a little bit of advocacy here, is the IFMRM RD, so the IFMRM raw data format. So this is a kind of accepted format for case-based data and for sharing of case-based data, a real sort of push from the community for reproducibility in reconstruction. So the Gadgetron uses this tool, but also there are a lot of other tools out there that use it. So if you aren't familiar with it, something to think about familiarizing yourself with. Really, it's sort of data stored in one of these HDF5 formats. There's an XML header, and then there's sort of like this raw data section that's more or less just a struct or a matrix of data. But as for our MRI LINAC application here, we want to increase this imaging speed. We want to see how fast we can image, how fast we can track, and with what boost our spatiotemporal resolution. So one of the things to really speed up MRI is to reduce matrix size. So we can do that easily on an acquisition side on an MRI scanner, but then we've lost resolution. So super resolution is a kind of an AI technique that allows us to artificially generate resolution. For those of you that aren't familiar with super resolution, I'd say that in particular, say these EDR-SR networks. So I'll say first, so super resolution, for those of you that aren't familiar with it, you might want to picture maybe 10 years ago, sitting down, you're watching a spy movie, someone has some CCTV footage of a number plate or someone's face and it's really blurry. And the big boss walks over and says, oh, can you enhance it? And someone pushed that magic button and they said, oh yeah, sure. And it goes, do, and then all of a sudden the face or the number plate flips into really high resolution. So super resolution, and at the time, 10 years ago, we kind of said, oh, that's just, that's kind of magic. That doesn't really happen. And now super resolution really has enabled huge advances in terms of what's possible in post-processing and image enhancement. So EDSR, enhanced deep super resolution, is one of the leading networks for this, and uses a bunch, for those of you that do AI stuff, uses a bunch of residual blocks and pixel shuffling to increase the resolution. So to give you an image here from the original paper, what you can look at here is using standard interpolation techniques. This is kind of the blurry bicubic upsampling you might get. This EDSR, and then there's a ground truth image here in the middle. This EDSR is what is kind of the performance difference between bicubic interpolation and what AI enables. So huge improvement that's very obvious just to the naked eye in upsampling images. So in our case here, what we did to integrate this AI super resolution to the MRI Gadgetron is we retrained the network on a bunch of brain cancer and lung cancer images, depending on the particular application. I'm showing lung cancer here. But yeah, so a bunch of just training the network on synthetically downsampled images from a 3 Tesla scanner. And then we essentially plugged this into our workflow. So we installed the Gadgetron on the computer. We then have the MRI scanner, it acquires at low resolution. The EDSR in the Gadgetron then upsamples that to really high resolution. And then with the tracking algorithm, that then feeds information back to the beam shaping device to track the tumor. To say a lot of this work was really made possible by my PhD student, James Grover. It's really leading the charge on making a great repository here as well, which I encourage you to check out. And then we characterize that we characterize the performance improvements using a bunch of error metrics, I guess, and different comparison techniques. Now, to show what some of those results actually look like, here is what we might expect. So this is a healthy volunteer being imaged, and here we're tracking the diaphragm in that healthy volunteer. So if we were to image with 64 by 64 resolution, we'd be seeing, this is what we see. I mean, this is real data. This is what we'd see in real time. But you can see that the 64 by 64 is by its very nature quite a low resolution image. Here we have 256 by 256 resolution, but the frame rate is quite slow. So our latency tracking on these images, as shown by a phantom experiment, is about 850 milliseconds, as opposed to here where the latency is closer to 300 milliseconds. Now, we can implement that EDSR, and then what we find is that we can, so this is an interpolation experiment here. So this is sort of your standard bicubic approach. And you can see that works quite well, but the images are quite a bit nicer using the EDSR, the super resolution approach. So that enables us to get this really kind of fast, high resolution imaging with AI. And if you look at the change in the latency here, it's only really adding about 5 milliseconds to the processing time. So it's almost extra information for free. And it corresponds to sort of about a 4 dB boost in the PSNR. And next up, we've got a nascent partnership with Genesis Care, which is a big radiation oncology company, to try and look at putting this onto a clinical MRI LINAC. Now, I thought I'd mention as well, now that we have this Gadgetron, we have all the AI technology, we have all these things integrated together, you can then start thinking about swapping other things in. In this case, implemented on the platform, not directly through the Gadgetron, but still implemented on the platform that we produced looking at motion prediction with LSTM. So in this case, the idea is that you can imagine a lung tumor might have a sort of semi-sinusoidal motion. And so if you know where it's been in the past, you might be able to predict into the future and adapt into the future. So these long short-term memory networks are some of the leading approaches for predicting into the future. In this case, it takes the last 8 positions of the tumor, or in this case, the diaphragm, and then predicts the next 2 time points into the future. And the idea is that if you use some time point in the future as your predicted location, that might aid the accuracy of your tracking. And so we implemented this on the MRI LINAC and found that it can really kind of increase the accuracy of treatments by up to about 40%, which translates to like kind of a millimeter or so, which can be a significant difference in some of these treatments. Now, changing direction a little bit here, but still on the MRI LINAC, I want to say that distortion in MRI grade radiotherapy is really not good. In particular, here I'm looking at, sorry, I lost my labels. On the top image here, we have a CT scan of a grid phantom, and then on the bottom, we have an MRI scan of the same phantom. So this is quite a long phantom. You can see once you get sort of outside of that diameter of spherical volume, the homogeneous DSD in the center of the magnet, the distortion can get quite significant. And in particular, so this is down to two real causes in this case, so gradient nonlinearities. So these are typically sequence independent. So that's when your gradients are not perfectly linear. When you get towards the edges, the gradient field you think you're applying is different to what you're really applying. And then on top of that, there are standard B0 inhomogeneities that can change your encoding. And these can be sequence dependent, very much depend on echo times and things like that. What I wanted to say here though, is that the current tools for measuring and correcting this distortion are really black boxes. And so in particular, Brendan Whelan, one of the members of our team, really pushed forward creating this MRI distortion toolkit that is an open source tool to really evaluate and ideally correct everything to do with your MRI scanner. We'll say it's available on PyPy, and I'll say a little bit more about it, but you can go pip install for yourself if you're a fan of Python. So what does this distortion toolkit do? The first bit is that we really found that these phantoms, distortion phantoms, are typically very heavy, very expensive. So the first thing was to kind of have a module that essentially allows you to go and construct your own distortion phantom for quite inexpensively. So what we find here is that and there are a bunch of suggestions on how to do this, but it enables you to create production files to send to a manufacturing company, in this case, for laser cut foam. And then into these holes, you insert fish oil tablets or paintball ammunition. And that allows you to create this array for imaging, and then you image it. And in this case, there's the CT scan that looks great, the MRI scan, and then the tool matches the markers for you, and you can see there's an offset. It crunches the numbers and it can characterize what's going on in the magnet. So in this case, you can see sort of B0 inhomogeneities across the DSB. And then there's a tool based on spherical harmonics to correct it. So you can go from a really distorted image to a much better image here. Now, of course, in terms of what I was speaking about earlier, we're really looking at ways to implement this distortion. In this case, some work from Shan, looking at unrolling networks. So they use a bunch of known MR physics to really kind of aim to open up this black box of deep learning. And in this case, there's a series of soft shrinkage thresholding blocks that incorporate data fidelity terms and a bunch of forward and backward transforms that reduce the image artifacts. Again, a repo there that you can go check out the code and how it works. But the point that I want to make is that these unrolling networks really incorporate Fourier transforms and known MR physics. They're modeled on compressed sensing into the reconstruction. And so what that means is we look here, here's some results on using it on some brain imaging. Now, these metrics, the NRMSE, the structural similarity, they are most improved for, in this case, this unrolling network, the DC Recon net, as opposed to distortion correction based on UNets. But UNets don't actually incorporate really any known MR physics. And so even though that's performing a little bit better there, what I want to make the point is that these networks that incorporate the MR physics are much more robust to domain shift. And so if we look here, this was trained on brains. If we apply it to this distortion phantom, we can see that this DC Recon net, which is correcting the distorted phantom here, and it gets this really beautiful, almost perfect image, I guess, to your eye. And compared to a UNet, the UNet is kind of distorted. So I guess the point I'm really trying to emphasize here is that we really believe that these networks are being developed in a way that they will hopefully, when used more out of domain on other MRI scanners, other vendors' platforms, they'll be robust to these domain shifts that plague AI deployment in particular. So looking very quickly towards the future, I just want to say for us, one of the things we're working on now is sort of vendor agnostic sequence programming as well. So in particular, some of you may have seen PulseSeq. So in this case, it's kind of the other side of the Gadgetron. It's rather than the reconstruction, it's the acquisition. PulseSeq generates this vendor agnostic file that then gets put into an interpreter for your particular platform. You can then simulate what the acquisition should look like in MATLAB. In this case, very recently, in the last couple of months, we've got it up and running on our MRI Linux. So in this case, we can simulate and show that the sequence is what it's meant to be, and then imaging a very basic phantom in this case. But I'm really looking to hopefully support some of the more cutting edge and acquisitions, but across vendors and implementing those. And then also to say that for the clinical translation, we're looking towards the Elector Unity, which is the best supported MRI Linac. There is a tool called ReconSocket that's developed by a team at UMC Utrecht. It's very much similar to the Gadgetron in terms of the architecture and the approach and enabling reconstruction, but it's not fully open source. Some of the a lot of the application is perhaps a little bit more challenging in terms of how you would go about doing it. So to wrap up, I'll just say that open source is enabling AI-powered tracking on our MRI Linac and really helping speed up this slow MRI modality. Something I wanted to say as well is just that support for all these different tools varies. So I was going to say be careful, but I think instead I would say just be considered. Ask questions about which tool is best first and what people's experiences are with support and things like that. And also to say sort of whatever your need is, there is probably already a tool for you. But if there's not, as there was with our sort of distortion correction stuff, build it and share it with the world. And that's what I hope we're achieving here. And thank you very much to all the people that made this work possible and the funding bodies. And thank you for your attention.